Ladies and gentlemen, so far we have assumed that all the answers we have been getting in linear programming, they are fractionals. It's possible for them to be fractionals. I'll give you an example. There was a marketing example that we did. That marketing example, we had TV to be 1.18, I think, 1.82. Then we had the radio advert to be 10. And then we had the newspaper ad to be 3.18. So those were decimals. So decimals means they are fractions. Okay, they are fractions. Now, because of this, we need to find a way to handle it, because you can't have 1.18 TV advert. You can't have 33.56 aircraft. You can't have 19.29 cars or vehicles. You can't. You need a whole number. You need an integer. An integer is a positive or negative whole number. In our case, we can't expect negative because we always want non-negativity constraints. Sometimes the temptation would be to round them up. But when you round up, down or up, suppose my profit is 38.18 billion, and then you decide to make it 38 billion. What about the 18 million? Okay, you can't just throw it away. So rounding doesn't really help. So what is it? We need a proper solution called an integer optimal solution. And this is going to be the same as the linear programming one. The only thing is that we are going to introduce something known as the integrality constraint. Now in the Excel, this is represented by int. You remember where you have to click in the solver and you have to select whether it is less than or equal to, greater than or equal to, equal to. There was another one called int, integer, and there was another one called bin, binary. So these are all of the possibilities that could happen. Godwin says, am I the only one having issues with your audio? Okay. If you're having issues with the audio, probably want to log out and log back into the show. Okay. So, somebody says works fine for me. So check your internet. All right. So we can have all of these. The best way to, so everything under integer programming is the same as everything under linear programming. The only thing is the integrality constraint. And the best way to make you understand is to give you an example. There are three main kinds of situation. Now, please note, when something is not an integer, it means that it can be fractions. Now, when it is an integer, it could be that, and this is important, it could be that the model you are formulating, that model has a portion being a binary. A binary means that it can be 0 or 1. Now, where 0 here means is not there, and 1 means is there. Okay. So, for example, you can have a binary constraint, say 1 or 0. So this will be the only possible answer. So xi can be 1 or 0. A typical example is gender. Gender is binary. Female is 1. Male is 0. So the moment I say, are you 1 or 2, and the person says 1, what it means is that he's not 2. And so that's a typical example of binary. So binary is just two possibilities, 0 or 1. But then you can also have whole numbers, mixed integers. Now, mixed integers means that some of them could be binary and some of them could be what? Could be integers. So for such ones, you just apply the integrality constraint for them, which means whole numbers. And then the other ones, you apply the binary constraint for them. Okay. So that is it. And sometimes you can have a situation where some of them could be decimals, some of them could be binary, and some of them could be whole numbers. Now, decimals means they can be fractions. Binary means they can be 0 or 1. And mixed means that they can be all of them. It can be, not just 0 or 1, but it can be 2, can be 3, can be 4, can be 100. So we're going to look at all of these examples. Okay. And let me take a first example for us to look at. This is a storyline. What we are going to do is that we're going to formulate this storyline. And then we will determine whether we are dealing with an integer or we are not dealing with an integer. So we are going to decide whether we got to use an integer constraint for this or we should not use an integer constraint for this. Okay. Now, normally when it happens that somebody's internet is echoing, like so many of you, few of you are saying that the thing is echoing. Actually, one person. If it is echoing, what it means is that it is from your end, because it cannot be echoing on my end. If you have turned yours on, okay, it will be echoing. If yours is not on, there wouldn't be any echoing on yours. Okay. So, but actually, so let's look at this story. We are going to write the story down. Okay. The story says Agbala, owner of a machine shop, is planning to expand, purchasing some new machine presses and lathes. Now, the word presses and lathes is an important thing because you got to understand what a press is and what a lathe is. You got to think whether this can be an integer or not an integer. When I say an integer, I mean whether it is a whole number. Okay. And obviously, you can't have 1.18 presses. Neither can you have lathes that are 1.15. So this is a typical example of an integer. You expect the lathes to be that. Okay. Now, each press will increase profit by 100. Each lathe will increase profit by 150. So what are the hundreds and the 150 standing for? Now, if you have mastered the linear programming, once again, it's from previous. You will know that these will be standing for the coefficient. And the fact that we are talking about profit here means that we are going to be maximizing profit. Now, the number of machines Agbala can buy is limited by the cost. Limited means that is the right-hand side of the constraint. So we are going to have less than or equal to by the cost of the machines and the available floor space. So again, this tells you that these are the resource constraints. Okay, and of course the data is here. This is the data. So when you look at press, it will require 15 square feet of floor space. Later will require 30 square feet. The purchase price, which is the cost of the press, is 8,000 and the lathe is 4,000. So this is the budget constraint. You can see the next sentence says Agbala has a budget of 40,000. So that should be on the right-hand side of the constraint. Now the simple thing is that Agbala want to know how many of each type of machine to buy. How many of it? So start thinking about what is going to be the decision variable. It's going to be let x1 be what? Let x2 be what? Okay. Now Agbala want to know how many of each type of machine to buy in order to maximize or increase profit. So what do you think is going to be the x1? You can type all of your answers now there if you know, because I'll be taking a few of these recordings to reward you marks. So what will be the decision variable? What will be the decision variable? Okay. So let's try to make sense. It says that let x1 be something. Let x2 be something. Now you will know from the sentence that x1 will be the number of presses to buy. Okay, so that will be the number of presses. Start thinking about the objective function. Okay. Start thinking about the objective function. The number of presses bought, and then this one will be the number of lathes bought. These are the machines. So that is your objective function. Sorry, that is your decision variables. So what do you think is going to be the objective function? Let's take you back to the story. The objective function. Okay, if you have been following, you can get that from here. 100, 150, blah, blah, blah. What is going to be the objective function? Let me see some of the answers I get. Johnny Kofi says Z is 100 plus 150x2, and that is a perfect answer. Okay, so it's going to be 100x1 and then 150x2. Now, my interest, I know you can do this, but my interest is to make sense of the integrality constraint. So the Z max is going to be 100 of the x1, which is the presses, plus 150 of the x2. Okay, let me just clear this. 150 of the x2, which is just late. Okay, so this is an objective function subject to some constraint. And you might remember that there was a first constraint which was called the budget constraint, and there was a second constraint which was known as the floor constraint. Okay, so you got to get that. Now, if you go to the storyline, let me see some of the answers some of you are giving. Okay, so some are giving some very good answers there. Let's go to the constraint. Now you can see that there is a floor constraint, which is the top one here. And then there is a budget constraint, which is on the right side here. So the floor constraint is 15 of the x1, and then 30 of the x2. And then this one will be 8 and 4. So that's the same thing you're going to write. Now let me just document that here. So you're going to have 15x1 plus 10x2 less than or equal to, and you might remember the floor space that was given, and it's always good to go back to know what you're doing. Okay. It is 200 square feet. This was given there. 200 square feet of floor space. So keep that in mind. So this will be 200. The other one, okay, is, and in case you may have forgotten, it was 8,000 and 4,000. So it becomes 8,000. It becomes 8,000 x1 plus 4,000 x2. Okay. Those are the constraints. And then the right hand side was 40,000 cities. That was a budget. Okay. 40,000. So you write 40,000. And then of course our non-negativity constraint. Okay. Our non-negativity constraint. Our non-negativity constraint, in case you've forgotten, is always x1, x2, and then finally greater or equal to 0. You know this already. Okay. x1, x2, greater or equal to 0. So we're going to write that non-negativity constraint here. x1, comma, x2, greater or equal to 0. But then we have to ask ourselves, is this an integer? Are these decision variables, are they going to be integers? Yes, because when you look at them, they should not be decimal. So you will add and integer, and that's all. Okay, and therefore it forces these to be what? To be pure integer constraint. Now you can go and solve it in Excel and then look at the result. When you look at the results, if you don't force it to be integers and you just do non-negativity constraint, you're going to get decimals. But when you force it to be integers, and one of the constraints, you have to force it to be integers. Okay, so you need to signal and use the word integer. When you are selecting these ones, okay, when you are selecting this one, the constraint, you have to select integer. Integer. Okay, and that is what you want to do. And you can see a bit of that in the slides. I don't want to go bore in showing you this in Excel. My interest is your ability to recognize that this is an integer. Okay. Let's look at another example. Another example. And this example, by the way, everything I did is here. So you can check it and then see. Now this example is a little bit tricky, so I want us to do it all together. I want us to do everything together. So let's take this example. It's an interesting example. And remember, I told you that you can have a situation where the x's are integers, like what we just did, which is 1, 2, 3, 4, 5, 6, 7, 8, all whole numbers. But you can also have a situation where it is binary. Okay. And then you can have a situation where some of them are decimals, but some of them are binary, but some of them are whole numbers generally. So let's look at this example and see where it falls into this category. Legon Council must decide, this is an important word, gotta decide on which of the 4 recreational facilities that you want to build. You have to choose among pool, tennis, athletic field, gymnasium in order to maximize daily usage. The key is you are maximizing daily usage by resident. The expected daily usage, the cost, the land requirement for each project is going to be shown below. So let's show that first. So if you look at the second column here, you have expected usage, which means that the number of people who are expected to use the swimming pool is 300. The number of people expected to use the gymnasium is 150. So you have all of those right there. I hope you guys can see me. Okay. The number of people expected to use this is what you have there. So you can see that this is the number of people expected to use the gymnasium. Now, how much is it going to cost to construct a swimming pool? 35,000. And you will need 4 acres of land to do that. You will need 4 acres of land to do that. And then for gymnasium, I'm just taking the first and the last. Okay. Gymnasium is going to require 150 people to use, but it will cost a lot of money, $90,000. And it would need 3 acres of land. So that's what you have there. Now let's see which ones are going to be used for the objective function and which ones are going to be used for the constraint. Now, we can appreciate that when we go to the next part of the question. Legon Council has $120,000 a budget. That is a cost. So it means that this cost is a constraint. And the limit is what? $120,000. Let's go up. It says it has $120,000 budget. And then you have 12 acres of land. 12 acres of land. So again, the land becomes what? Another constraint. So everything here is going to be part of that constraint right there. Okay. The next thing. And the next thing is a very tricky thing, and we shall look into that deeply. Because swimming pool and tennis must, the word must is important, because swimming pool and tennis must be built on the same part of land. Only one of these two can be built. Okay. They must be built, but only one can be built. And finally, the Legon Council want to know which facility to construct in order to maximize the expected daily usage by residents. So the first thing we want to do is, what are our decision variables? What is our decision variables? How will you write the decision variables? How will you write it? Okay. How will you write it? You can raise your hand if you want to really talk the answer, or you can type the answer right in here. How will you write the decision variable? It's a very simple thing. Okay. So So let x1, let's go to the next page. Okay, somebody want to talk. So let's give somebody a chance to talk. Okay. Kelly. Yes, Kelly, go ahead.
Let x1 be number of pools, x2 be number of tennis centers, x3 be number of athletic fields, and x4 be number of gymnasiums.
Okay. So all I heard was, let this be the number of this, the number of this, the number of this. So number of swimming pool, number of that, number of this. Okay. Now you will notice that that will not be the right thing. And why is that so? Well, let's go up and then you see. Okay. Because you see, first of all, that word number of cannot be, because you say Legon Council must decide which of the 4 recreational facilities to build. So if it is which of them to build, we are not talking about the number of what to build. It is either you are going to be built or you are not going to be built. Okay. So if you look at this story here, okay, Legon Council want to know which, again, that sentence came, which facility to construct. That word is important. Which facility to construct. So if it is which facility to construct, it's like if I'm constructing this facility, I might not be constructing this facility. So there's a possibility of a facility to be constructed or not. And therefore, your decision variable will be the construction of that facility. Okay, it's not the number of it. Because you got to know whether you're going to be constructed or not. That's the most important thing. So this is a typical example of a binary, integer programming. A binary integer programming. So the decision variable is going to be this. Okay, it's going to be let x1 be the construction, and I normally want to write it for you so that you can appreciate it next time. The construction of a swimming pool. Okay, let x2 be the construction of, and the other thing was tennis. Okay. The swimming pool, tennis center. So the construction. Let me clean this first. The construction of a tennis center. The x3 becomes the construction of athletic field. Okay. And then x4 becomes the construction of a gymnasium. So this is what the decision variable. It's not the number of, because this thing is which to construct. It's not the number of it, which to construct. And we expect the answer to be either 0 or what? Or 1. Okay. Where 1 here represents what? You can tell me. You can type it like that. Okay. The values of this thing is going to be 0 or 1. Where 1 here represents what? If it is 0, what does it represent? If it is 1, what does it represent? Let me see whether somebody has documented that. If it is 0, what does it represent? Okay. If it is 0, what does it represent? If it is 1, what does it mean? Okay, Bismarck says that 1 means... No, and I'm not talking about that. I'm not talking about the numerical value. If it is 1, I like the answer Bismarck is giving. If it is 1, it means that we are building it. If it is 0, it means we are not building it. Okay? So it's not about integer or that. If it is 1, it means we are constructing it. If it is 0, it means we are not constructing it. It's just like if you are 1, you are female. If you are 0, you are... Okay. So this is something which is there or is not there. It's not about the number of how many of it is there. No. It is whether it's there or it's not there. Binary. You got to understand binary a lot. Okay. So now that we got that, we're going to write our objective function. And the objective function, okay, if you can go back here, it says in order to maximize the expected daily usage by resident. Expected daily usage by resident means that we're going to use the information here to write our decision variable. So that's what we're going to use. the information at the section right here. That's what we are going to be using to be, doing our analysis. So we are going to deal with this information for our decision variables. So that means that we are going to write our decision variable, and again, it's going to be Z max because we are maximizing the people, the expected daily usage. So it's going to be Z max 300 x1, 90 x2, actually 400 x3, and then 150 x4. That's what our decision variable is going to be. All right, so let's document that. Let's document that decision variable story. So we go to our construction element, and then we are going to write that there. Okay. Let me use a different color for this purpose because it's an interesting purpose. So our Z max is going to be 300. You got to be writing this while I'm writing. It helps you. It really helps you to 300 x1 and then plus 90 x2 plus the next one, if you can remember, was 400 x3, and then finally plus 150 x4. Now, okay. So once you've done that, then you do subject to the constraint. Leonie Kelly has documented that perfectly in the graph for us. Then you bring your subject to. The first subject to was the budget constraint. Let me just take it back quickly, okay, to look at that budget constraint. So that's it here. Okay, that's a cost. Okay, so we're going to have this cost constraint. Okay, 3510, 2590, and then we'll have the land constraint here. Okay, that one too is 4273. So we're going to write those constraints inside our constraint section. Okay. So the first one is going to be 35,000. To be honest with you, it's in thousand, but let's write that. 35,000 x1 plus 10,000 x2. Okay. And then you had what? 25,000 x3. 25,000 x3. And then 90,000 x4. Less or equal to, you can remember, is 120,000. That was a budget available. $120,000. And then, of course, the acres of land was 12. The total acres of land. Let me take you back to the storyline. So you can see that the Legon Council has 120,000 budget and then 12 acres. 12 acres. Now, what are the decisions for the land requirement? 4273. Okay, 4273. Those are the requirements. So you just write that constraint for that. Okay, 4273. And the total was 12. So it becomes 4x1, 2x2, 7x3, and then 3x4. You bring the pluses in between. Then we have to write our non-negativity constraint, which is x1, x2, x3, x4, greater or equal to 0. And this time, instead of doing and integer, you can rather do and binary. Okay. You can just do that to indicate that these are binaries. Now, if some of them are binary and some of them are integers, that one you have to specify. Okay. And that's it. Once you've done this, you are indicating that these things are either going to be 0 or 1 in that regard. And then you will be sorted in the final situation. If you check the constraints, that's it. But there was a constraint. Let me just take you back. look at this. The preamble said, okay, let me just take it back. It says that, and I hope you can see the slides. Yes, you can see the slides. The preamble says that because swimming pool and tennis, now swimming pool is X1. Tennis, we just go back up there, and then you know what tennis is. There you go. Tennis. What's that? Okay. I've just jumped to swimming pool. Tennis is X2. Swimming pool is X1. So let's go to the question. It says that because swimming pool and tennis, X1 and X2, must be built on the same part of land, only one can be built. Now let's quickly do this. Only one can be built. Only one can be built. What does that mean? Well, first of all, it means that when you look at the land parcel, swimming pool and tennis must be on the same land. But you can't put them on the same land. You can't put swimming pool and tennis on the same piece of land. Now, let me tell you why you can't do that. Because when you go to the land requirement for swimming pool, it is what? 4. And the land requirement for tennis is what? 2. So it means that you can't put the 4 and the 2 on the same piece of a land, because the land that is there, that particular land that is there cannot handle 6 acres. It's not able to handle 6 acres. So the question is, only one of these can be built. So how do you write that? Only one can be built. Now, let's document that, because that is a constraint that we're supposed to include. So that constraint will have to be there before even the non-negativity constraint. So how do you do that? Now, the first thing you want to understand is this. Must be built is different from can be built. So this is a contingency constraint. It's a contingency clause. Okay. Either you are swimming, you are taking swimming pool, or you are going for tennis. Okay. So I want to document that here. It's either X1 or X2. The word or is plus. Or is plus. Okay. So either you are doing this or you are doing that. So what does that mean? Okay. So this means that X1 or X2 can be constructed. In other words, the word can be constructed means has a value of 1. Remember, for you to be constructed, you must have a value of 1. If you are not being constructed, you must have a value of what? 0. Okay. And so X1 or X2, one of them can be what? Must be what? 1. 1. So we're expecting 1, the number 1 somewhere. Now the next thing is or. Or means that it is add. Okay. Or means add. And so it means that we are going to have X1 or, which is plus X2. And there's something in there before the 1 on the right hand side. Now what is that something in there? Okay. Now the word something in there before, now if you rush in, you rush out, you make some heavy mistake. I know some of you are writing some good answer, which is great. But you're going to see that some of you are going to be wrong. Okay. Because the statement says, okay, so first thing, or is what? Is add. But look at the sentence. The sentence says, because they must be built, but only one can be built. So that word can means that, must. Must is what? Equal to. Okay, so it must be built means it must be equal to 1. But it didn't say that. It says that only one can. Can means what? Can means that less or equal to 1. Okay. So only one can be built. So that constraint becomes X1 or X2 can be equal to 1. X1 or X2 can. And that is less than or equal to. Okay. Of course, this is a very tricky one. It's called mutually exclusive constraint. mutually exclusive constraint. This is the harder part of that very one. But this is a little bit tricky, but once you understand it, you know. Remember that or is add and must. Sometimes we use the word exactly. Exactly is also equal to. At least is greater or equal to. At most is less or equal to. Can is less or equal to. Must is equal to. So once you understand this, you will be able to now appreciate it. Now I'm going to show you some possibilities that could have happened. Anyway, what we did is here. Okay, this is what we just did, which is in your slide. Now let me give you scenarios so to see whether you can do this. What if the Legon Council says either swimming pool or tennis must be built, but not both? What constraint is that? What if they say that either swimming pool or tennis must be built, but not both? What if they have said that? What would you have? How would you have formulated that? How would you have formulated that? Either swimming pool or tennis must. Let me see whether I can get some hands. Is it Mandela? Mandela, tell us your answer. Yes,
so it would have been x1 plus x2 equals to 1.
Say that again.
x1 plus x2 equals to 1.
Correct. Excellent. Okay, that's how you would have been. Okay. And that is indeed something that we mentioned before now. Okay, x1 plus x2 equal to 1. That's exactly what it would have been. And so it's your understanding. It's understanding. So this one, it is forcing you to choose between the two. And this is known as multiple choice constraint. Okay, now let's take another one. Now, what if, I'm going to give you some examples, okay? Suppose you have gotten this constraint, exactly 2 of the 4 projects must be built. Who can think and tell me what this will be? Exactly 2 of the 4 projects must be built. Exactly 2 of the 4 projects must be built. How do you think you construct this? Exactly 2 of the 4 must be built. What would that have been? Exactly 2 of the 4 projects must be built. Remember what I told you about exactly 2. What did I tell you about exactly 2? You can guess what this constraint will be. Okay. Good. Is equal to. So now we're expecting equal to there. Backman, that's good. Exactly 2. Okay. Now that word now is he's not telling you exactly 2. Exactly 2 means that equal to 2. That's what it means. Exactly 2 means equal to 2. So you keep that in mind. So that will be on the right hand side, equal to 2. So what will be on the left hand side? Something should be equal to 2, exactly 2. So what should be on the left hand side? Excellent and better, that's it. The x1, the x2, the x3, the x4, they are the one who must be on the left hand side. They are the 4 projects. Okay? So what this means is that the 4 projects here, okay, this is x1, x2, x3, x4 equal to 2. Okay? Now this is an interesting one. Now what if you have this constraint? Let's go on. No more than 2 of the 4 projects must be built. Okay. No more than 2 of the 4 projects must be built. What would that be? What to be on the right hand side? No more than 2 of the 4 projects. What to be on the right hand side? What symbol and what number? No more than 2. What symbol or what number? Of the 4 projects, that one we know that is going to be on the left hand side. X1, X2, X3, X4, we add them. But what is going to be on the right hand side? What is going to be on the right hand side? Someone says less than or equal to 2. That is a correct answer. Less than or equal to 2. That's no more than 2. Perfect. Perfect. So that's how it's supposed to be. And that's this. Okay. Now let's take the final one. This is tricky. This is the last one. This is tricky. This is the last one. If swimming pool, which is X1, is very important, and tennis, which is X2, is less important, what does this constraint mean? How would you have written this? Swimming pool is very important. And X2 is less important. Not that it's not important, but it's less important. So in other words, one is more important than the other. But I didn't use the word one is more important than the other. I say one is very important, the other is less important. Okay. So what symbol are we looking at? What is going to be the link there? Okay. Now this one is either you know or you don't know. Okay. It can never be equal to here. There will never be equal to. There will never be greater than 2. Yeah, people are writing things. Talata is writing interesting things. Okay. So first of all, swimming pool is what? X1. So let's put that one down first. Okay. Let me just document that. Swimming pool is X1. So let's write X1. Okay. X1. Now it says that X2, that is what? What do you call it? X2 is tennis. So you put that X2 down. Okay. And then it says that one is more important. So swimming pool is more important than the other. So if swimming pool is more important, you have what? Greater than. Okay. But that will also mean that the X2 is what? Relative to the swimming pool. Oh, sorry, X1. That will mean that the X2 is what relative to the X1. Okay. Who can tell me? What will be the link between the X2 and the X1 now? What will be the link there? Less than. Less than is wrong. Okay, the link will not be less than. Okay. What will be the link? Less than or equal to. That's the right answer. So the link will be less than or equal to. Less than or equal to. So now let's go and see. And that is how it's going to be. If you understand some of these principles, it will help you. In fact, it will even help you next semester when you are doing a lot of things there. So this is it. X2 less or equal to X1. X2 less or equal to. This is a conditional constraint. Of course, these are technical part. These are the hardest part. Okay, but these are tougher ones. But at least you are learning. Now let's look at the last one. I've said the last one many times. What if swimming pool should be built? If and only if tennis center must be built, and vice versa. Swimming pool should be built if and only if tennis must be built, and vice versa. This one is simple. This is co-requisite constraint, simple, easy. Swimming pool gotta be there only if and only if tennis gotta be there. What is that going to be? This is simple. Excellent, excellent. Okay, excellent. I'm better. Excellent. George. Excellent. Bismarck. Excellent. Okay, I'm recording all of those typings. Very good. So that is it. Okay, you have equality there. This is equality principle, and there is no question about that. So this is our final formulation. Maximize this, subject to this and that. Okay, and then that mixed constraint is this, and then finally we had the non-negativity and then the binary constraint. Now that statement 0 or 1, you could have said that, okay, greater than 0 and binary. When you use the word and binary, then you don't bring or 1. But when you say, or you can say or 1 binary. Okay. But I like to use and binary, which means that binary here, it means that it's going to be 0 or 1. But you see, you've already said that greater than or equal to 0. In fact, this is better. This is better because once you say greater than or equal to 0, you already have the 0. So the next thing is, what is the next one? Because if you leave it in binary, it could be 0 or 12 or 0 or 6. So it should be greater than or equal to 0 or 1. 0 or 1 binary. 0 or 1 binary. Okay. So that is it. Okay. This is another one. I will encourage you to go and do it on your own, because today, what I want to do to you is to teach you a very important topic known as the fixed charge. The fixed charge. And at this stage, the fixed charge is very deep. And because it's deep, I will encourage you to go and do this last one. This last one, the most important thing is deciding which one of this is binary, which one of this is not binary, which one of this is whole number, which one of this is decimal. Simple. But there's not even binary here. There's no binary here. Okay. Because this is mixed. So either it's going to be decimals or not decimals. That's all. Whole number or not whole number. So even without reading, you will know. Building. Is it integer whole number or is not? Building. Is it integer whole number or is not? Type it there. Building whole. Is it integer? Building. Building. Is it integer? Is it integer? Building. Is it integer? Yeah. Building is an integer. Building is a whole number. What about land? What about land? What about land? Land. Land. Is it integer or is not integer? Land. Land is never an integer. You can have a quarter plot. Don't you know that? You can have a quarter plot. You can have 1.5 piece of a land. You can have square feet of a land. You can have decimals of land. Okay. You can have, I have 2.5 plots of a land. I have 2 1/4. That 1/4 is a decimal. It's not a whole number. Okay. So land is can be decimals. Now bonds, and I'm talking about bonds, the paper bond, the paper you are holding. That one is a whole number. I don't want you to think too much. That one is a whole number. So building is a whole number. Land is not a whole number. Bonds is a whole number. With that in mind, you can now formulate your analysis. So do that on your own. And now I'm going to show you how to do the next stage. So if you do all of this formulation,